Hello guys, welcome back. In this video, I'm gonna talk about how to use R to perform text analytics. Nowadays, textual data is everywhere online and is a wonderful resource to mine. But it's a challenge for businesses to keep on top of all the tweets, emails, reviews, and product feedback that pour in every day. If we can teach computers to understand texts, we can then drive them to read thousands or even millions of texts to learn, for example, the general public's opinions on your firm's products or services, as computers are extremely good at repeating things. This vision is attractive, and the path to achieve it is text analytics. To start, let's first get an overview of the text analytics workflow. The text analytics workflow starts with obtaining online text sources. And once text sources are identified, we can start extracting documents and building the corpus. Typically, this step stores the text as a raw character string with metadata and details stored with the text. Once we have acquired enough documents, we can step forward to do transformation. In this step, we want to remove extraneous information from the text and standardize it into a uniform format. This process typically involves case folding, a common strategy of which is to reduce all letters to lowercase, punctuation and number removals. Since punctuation marks and numbers are generally not useful features. Stop word removal. Stop words are common words that are not informative as the, of, to, and so forth in English. They are not useful for analysis. Stemming. In information retrieval, stemming is the process of reducing inflected or sometimes derived words to their word stem, base, or root form. And the next step is feature extraction, which involves converting the text string into some sort of quantifiable measures. The most common approach is the bank of words model, whereby each document is represented as a vector which counts the frequency of each term's appearance in the document. We can combine all the vectors for each document together, and we can create a term document matrix. And once features are ready, we can perform a variety of analysis, including text classification, sentiment analysis, topic modeling, etc., with text. The R toolset we are going to introduce for text analytics is the Tidy Text package. The Tidy Text package provides many useful functions for text analytics. For example, the honest tokens for tokenization, byte TF IDF for calculating and binding the term frequency and inverse document frequency, cast DTM for calculating the document term matrix. It also provides many useful data sets. For example, the stop words dataset for stop word removal, and the sentiments dataset, which contains a dictionary of sentiment associated words. This package also provides an inherent support for tidy data format and allows seamless conversion of text to and from tidy formats. So when using it, we can switch seamlessly between tidy tools and existing text mining packages over the course of text analytics. I'm going to use the GenR package to demonstrate the standard workflow for text analytics in R. The Jane Austen R package provides the text of Jane Austen's 6 published novels in a one-row per line format, where a line in this context is analogous to a literal printed line in a physical book. The Jane Austen R package has a function named Austen Books that returns a tidy data frame of all of the 6 completed novels. Let's start with that, and also use the mutate function to annotate a line number quantity to keep track of lines in the original format, and a chapter to find where all the chapters are. Here, the regex function is a string_rs modifier function. It controls the actual matching behavior defined by a regular expression. Here, we set the ignore case option to true, allowing characters to match either their uppercase or lowercase forms. Within the tidy text framework, we need to break the text into individual tokens. A token is a meaningful unit of text that we are interested in using for analysis. An example of tokens includes a word, an n-gram, a sentence, a line, and so on. To tokenize the text, we use the onNestTokens function in the tidy text package. This function tokenizes the text by coupling the units of text and transform it into a tidy data structure. Here we use the default unit, words, for tokenization, and specify the name of the output colon to word and the name of the input colon to text. So we end up with a new data frame with each observational unit corresponding to an individual word. onNestToken also strips all punctuation marks and converts each word to lowercase for easy comparability. Sometimes it could be useful or necessary to look at different units of text. Then we can use other tokenization options, such as characters, n-grams, sentences, and so forth. Here, I tried 2 alternatives. One is to tokenize text into sentences using the built-in option. And the other is to tokenize text into chapters using a regular expression. Next, I'm going to remove stop words that are not useful for text analytics. Tidy text has a dataset named stop words, which stores English stop words. We can use anti-join or filter to remove these stop words. Now, the data is ready for some basic analysis. To motivate an important type of text analytics, the sentiment analysis, let's consider these 2 user reviews from the IMDb website. As human beings, we can easily capture the sentiment expressed in each review when reading it, and even infer some nuanced emotions its reviewer was experiencing when she or he wrote the review, like surprise, disgust, boredom, or excitement. With a moment of introspection, you may realize that what you actually rely on to determine the sentiment of a review are several keywords with emotional intent. So perhaps we can apply this idea and use the tools of text mining to approach the emotional content of text programmatically. Sentiment analysis is a type of text analytics that draws upon positive and negative word sets that convey human emotion or feeling. One way to analyze the sentiment of a text is to consider the text as a combination of its individual words. And the sentiment content of the whole text is then considered the sum of the sentiment content of the individual words. Then, how can we know the sentiment content of individual words in the first place? Well, there are a variety of lexicon or dictionaries that exist for evaluating the opinion or emotion in text. These lexicons contain many English words, and the words are assigned scores for positive or negative sentiment, and also possibly emotions like joy, anger, sadness, and so forth. The tidy text package provides the function getSentiments to get several most commonly used lexicons. Here are two examples. The Bing lexicon categorizes words in a binary fashion into positive and negative categories, which means this sentiment colon takes on binary values, either negative or positive. And the Anfing lexicon assigns words with a score that runs between -5 and 5, with negative scores indicating negative sentiment and positive scores indicating positive sentiment. Another lexicon that I didn't display here is the NRC lexicon, which groups words into fine-grained categories of nuanced emotions like anger, anticipation, disgust, fear, and so forth. You may wonder, how were these sentiment lexicons put together and validated? Well, they were constructed while either crowdsourcing or by the labor of one of the authors, and were validated using some combination of crowdsourcing again, restaurant or movie reviews, or Twitter data. Given this information, we may hesitate to apply these sentiment lexicons to styles of a text dramatically different from what they were validated on, such as narrative fictions from 2000 years ago. While it is true that using these sentiment lexicons with, for example, Jane Austen's novels may give us not very accurate results, we can still measure the sentiment content for words that are shared across the lexicon and the text. And you may also notice that not every English word is in the lexicons. This is a correct observation because many words are pretty neutral and thereby excluded from these lexicons. Now, we are ready to do the sentiment analysis with the Jane Austen's novel data. Here, I'm using the inner join function to remove all neutral words and keep only the positive and negative words identified by the Bing lexicon. Next, I'm going to define the size of sections for which the sentiment will be measured. The size of sections that we use to end up sentiment scores can have an effect on our analysis. Small sections of text may not have enough words in them to get a good estimate of sentiment, while really large sections can wash out the narrative structure. For these books, using 18 lines works well. So here, I use the integer division to define sections of text that each span 18 lines. And we also count up how many positive and negative words there are in defined sections of each book. Next, I use the pivot wider function so that we have a negative and positive sentiment in separate colons. The positive colon contains the count of words in different sections that match up with the list of positive words in the Bing lexicon, while the negative colon contains the count of words that match up with the list of negative words in the Bing lexicon. And lastly, I calculate a net sentiment by subtracting the count of negative words from the count of positive words, and using the result as the net sentiment score. Now, we can plot these sentiment scores across the plot trajectory of each novel. And we can see from this figure how the plot of each novel changes toward more positive or negative sentiment over the trajectory of the story. One advantage of having the data frame with both sentiment and word is that we can analyze word counts that contribute to each sentiment. By using the count function, we find out how much each word contributed to each sentiment. However, we can spot an anomaly here. The word miss is coded as negative, but it is used as a title for young, unmarried women in Jane Austen's works. So it is appropriate for our sentiment analysis purpose. A possible solution could be adding miss to a customer stop words list so as to remove it from the analysis. There are other interesting plots for text analytics. For example, we can use the word cloud package to draw word clouds. This package also provides a comparison cloud function, which allows us to color positive and negative words differently and visualize both frequencies and sentiment contents of words in the same plot. So far, we've considered words as individual units only. Lots of useful work can be done by tokenizing at the word level, but sometimes it is useful or necessary to look at different units of text. To help you see the need to go beyond words or unigrams, let's look back at our movie review example and see how unigram-based sentiment scores play out when related to known ratings. This table suggests that they may not be doing so well. These sentiment scores are missing favorable ratings of Marigolds and Find Me Guilty, as well as unfavorable ratings of Morning Ball. The main drawback of unigram-based measures is that they only focus on the presence of a word, while ignoring the context of the word completely. In fact, a word's context can matter nearly as much as its presence. A good word can be used in a sarcasm setting, and a bad word used in a negated text could mean a praise. It would be easy for us to review a bad movie using words chosen from the positive list, or a good movie using words chosen from the negative list. There is nothing inherently good about positive words, or inherently bad about negative words. As with any words we might use in communication, it is context that gives them meaning. And many interesting text analyses are based on the relationships between words. For example, which words tend to follow other immediately? In a sentence like, I'm not happy and I don't like it, the words happy and like will be counted as positive, because unigram-based measures cannot take into account negating words before these words. More subtly, in this example, the adjective unpredictable may have a negative orientation in our automotive review, in a phrase such as unpredictable steering, but it could have a positive orientation in a movie review, in a phrase such as unpredictable plot. Although an isolated adjective may indicate subjectivity, there may be insufficient context to determine semantic orientation. Moreover, the sentiment content of a word could also depend on non-consecutive words, as exemplified by the word lead in these two sentences. Therefore, in order to capture the bits of context that can help analyze sentiment, we should go beyond unigrams, and the sequences of consecutive words might capture structures that isn't present when we just count single words, and could provide context that makes tokens more understandable. And we can further use modeling techniques to learn about them. Capturing relationships between words require tokenizing by sequences of adjacent words. Unnested tokens can tokenize text into n-grams using the n-grams option and setting n to the number of words we wish to capture in each n-gram. Let me use bigrams to demonstrate how to take into account the effects of negating words in sentiment analysis. Once we get bigrams, you may find the most common bigrams are pairs of stop words. So in order to remove cases where either word is a stop word, we need to first use the separate function from tidyr to separate the bigrams to their constituents. Then use the filter function to remove cases where either word is a stop word. And lastly, use the unite function to recombine them into one bigram. So this workflow lets us find the most common bigrams not containing stop words. Performing sentiment analysis on bigrams allows for examining how often sentiment-associated words are preceded by negating words. Here, I first use the filter function to zoom in on a set of bigrams starting with any of these four negating words. Then use the inner join function to drop all neutral words and keep only sentiment-associated words identified by the Alpine lexicon, and count their frequencies and assign them sentiment scores by negating the sentiment scores of the corresponding sentiment-associated words. Then, for each negating bigram, calculate the product of the sentiment score and the frequency as a proxy of its contribution to sentiment values, and select 10 bigrams which have the greatest contributions in either a positive or negative direction for each of the negating words. We could further visualize the words which have the greatest contributions for each of these four negating words. And this analysis reveals how finding consecutive words can give context to text mining methods.